Okay, a particle of mass m falls from rest at a height h, should say h, I think. At a height of, I'll just put that in, h, and experience a resisted force, so experience a resisted force of minus m kv squared. Let Vt be the terminal velocity and show that the acceleration is g minus kv squared. Okay, so let's just do that part first. All right, so the particle falls from rest, so that's v equals 0, and it's going to fall from, we're going to put x equals 0, so we're going to make positive going down and negative going up, and time equals 0. Okay, so we've got this particle. The weight mg will be going down, so that'll be positive, and the resistance force is minus mkv squared. So the sum of the forces would be minus mkv squared plus g, and that has to equal mass times acceleration. Minus mkv squared plus g. Oh, mg, sorry. mg. So if you divide by m, then you end up with acceleration is minus kv squared plus g, or g minus kv squared. And that's the required result of the first one. Okay, so that's part A. All right, part B. Show that Vt, find Vt squared, where Vt squared is the terminal. That word's been chopped off. Oh no, velocity, terminal velocity. Okay, so let's look at that. Well, the terminal velocity is when x double dot equals 0, because it's when the velocity reaches its absolute maximum. So g minus kv squared equals 0, g equals kv squared, v squared equals g over k. And that would be the terminal velocity squared. Okay, so that's all good. Now part C. The particle hits the ground with a velocity of w. Show that the distance travelled h is given by that. So we start off with x double dot equals g minus kv squared. And because we want the distance, we go dv on dx equals g minus kv squared. We bring all the v's together, which should be that, and that's 1 dx. And then we're going to look at integrating that. Now, when we integrate that, we know it starts with v equals 0. Okay, and the particle, so what does it say? It hits the ground with a velocity of w. So that means that the velocity final would be w. So it goes from 0 to w. And the distance here goes from 0 to h. Okay, so let's go. All right, so to integrate this one, it is a log, because you can create the derivative as minus 2k v. So you divide by minus 1 on 2k. So minus 1 on 2k is ln of the bottom, which is kv squared. And the derivative of 1 is x, and we're going from h to 0, so it's h minus 0, which will just be h. And this one here will be 0 to w. Okay, so that means we've got minus 1 on 2k ln g minus k times w squared minus 1 on 2k ln g minus k times 0 squared equals h. So it is minus 1 on 2k ln g minus k w squared plus 1 on 2k ln g equals h. Rearrange that, so that's ln g minus 1 with a 1 on 2k ln g minus kw squared equals h. So if you take the 1 on 2k out, when you subtract the logs, you divide the numbers, so that's g on g minus kw squared. Now, what are we aiming to get to? If you go back up, we're aiming to get to mu squared plus vt squared over vt squared. Oh no, I'm looking at the wrong one. Vt squared over vt squared minus w squared. So let's just write that down. So it's 1 on 2k. This is what we're aiming to get at. 1 on 2k ln vt squared over vt squared minus w squared equals h. So this is very close. Notice there's nothing in front of the w here, and here it has a k. So if I go through and I divide everything by k, and what does vt squared equals? Remember, it's g over k. So it's 1 on 2k ln. Now I'm going from this one, g over k over g over k minus w squared, because the k's will cancel, equals h. But that means it's 1 over 2k ln vt squared over vt squared minus w squared equals h. Okay. Alright, so that gets the first part. Alright, let's just have a look at the next question. Okay, so if we look at the next section, which is this, the particle is projected upwards now. So we've got it in that's in exactly the same medium, but what happens is plus is up and minus will be down. The height will still remain the same as high, but we're calling it V max in this question. V equals 0 when it hits the top, and it starts with a velocity of mu, and it still gets the same resistant force. So we've got mg for the weight, and the resistance force is minus kmv squared. It'll still be negative, it's because it's going downwards against the motion, which is going upwards. So the sum of the forces is minus mg minus mkv squared. So mass times acceleration is minus mg minus mkv squared. M's go out. Acceleration is minus g minus kv squared. Okay. So now what that means is we have minus g minus k plus kv squared. And because I want to get the height, I'm going to go v times dv on dx. So if you group the v's together, you get v on g plus kv squared dv equals minus 1 dx. Now when we integrate this one, so it starts at v equals u and finishes at v equals 0 when it reaches the max, starts at x equals 0, and it goes up to the height, which is the max. Okay, so we're going to go from 0 to the height, which is 0. And then we're going to go from mu up to 0. Okay, now how do you integrate this? Well, the derivative of this is 2k, so you put 1 on 2k, and it is just a log. So it's 1 on 2k ln g plus kv squared, and we're going from mu up to 0, and this is x, and we are going from, I don't know why I put 0 there, we are going from 0 up to h max. So 0 up to h max. So when you put that in, you just get h max because it's minus 0. And on this side, we go a half 2k ln. So it's ln g plus 0 minus ln g plus k mu squared. Alright, so it's 1 on 2k ln g on g plus k mu squared equals h. I know what I forgot. I left this negative out of here of the x because that's negative 1. So that would be minus h, so that's minus h. And that means that when I bring the minus over to there, it's 1 2k minus ln g on g plus ku squared equals h max. And then the minus here will just, when I bring that up as an indice, it'll flip it. g on ku squared to the minus 1 equals h max. It's a really handy thing to know that if you have ln on AB, if it's the wrong way around and you really want it to be B on A, what you can do is if you put a minus sign here, it will flip it. And all you need to do is change the sign at the front. So if I bring the minus 1, it flips it to ln B on A. So that's what's going to happen here. I get 1 on 2k ln g plus k u squared on g equals h max. Now this is very similar to what we want, except it's 1 on 2k ln, and it's got vt squared plus mu squared on vt squared. So you want the terminal velocity in there. So let's just have a look at what the terminal velocity is. Vt squared equals g over k. So this is very similar. All that I need to do is divide each of these terms by k. So if you take this one here and you go 1 on 2k, you have ln, so you have g on k plus k mu squared on k over g on k. So I'm dividing top and the bottom by k. Then what will happen here is you will get 1 on 2k ln g on k plus mu squared, because the k's go out, on g on k, which is h max. And if you look at the g on k part, you can just replace it with vt squared, and then you're going to get your required result. 1 on 2k ln vt squared plus mu squared over vt squared, which is equal to h max. Okay, so now we've also done this. We've found that. We've found this. Okay, and then the last part we want to do is manipulate this. So we want to prove that. So in order to prove this, the height up will equal the height down. So that means that this one, which is 1 on 2k ln vt squared on vt squared minus w squared, that one would have to equal this one here, which is 1 on 2k ln mu squared plus vt squared on vt squared. So if we make these two things equal to each other, ln vt squared on vt squared minus, there's a minus w squared, because it's the same height up and back, is 2k ln mu squared plus vt squared on vt squared. The 1 on 2k's will go. The ln is common in both, so that would also cancel. So that means that vt squared on vt squared minus w squared equals mu squared minus plus vt squared on vt squared. Okay, so the vt4 will cancel, so that's that and that. And then these ones here are negative, so I'm going to move them over to the other side. So you have 0 is vt squared mu squared minus w squared mu squared, w squared vt squared. Bring them to the other side, so you get w squared mu squared plus w squared vt squared equals vt squared mu squared. So what our prize is, what we're trying to get is 1 on w squared is 1 on vt squared plus 1 on mu squared. So the 1 on w squared would have to match up with that. And the only thing that's actually missing there is the w squared. So if I go through and I'm going to divide everything by vt squared mu squared w squared, vt squared mu squared w squared, let's just have a look what will happen. So the mu will go with the mu, the w with the w, and you're left with 1 on vt squared. The vt squareds here will cancel, the w will cancel, you're left with 1 on u squared. Vt squareds cancel here, u squareds cancel there. And when you have a good look at what's actually left, you have 1 on vt squared plus 1 on mu squared and 1 on w squared, which is what our prize is, which is our required result. So it's actually proven. Now the very last part, so that part's done, we have to say W equals UVT over the square root of U squared plus VT squared. And the last part is just to prove this, okay? So if we take what we've got there and we go mu squared plus VT squared, and we get a common denominator, VT squared U squared equals 1 on W squared, then it enables us to flip it. So it's VT squared mu squared over mu squared plus VT squared. And then all we need to do is square root it. Now we only take the positive square root because W is the velocity in the positive direction as it's falling. Okay, so when you square root the top line, you get VT mu, and the bottom is just the square root of U squared plus VT squared, which equals W as required. Woohoo.